Section 4.1, Introduction to Exponential and Logarithmic Functions. Part 1, Introduction to Exponential Functions. A function of the form f of x equals b to the x, where b is a positive real number and b does not equal 1, is called an exponential function with base b. Identify the base of each of the following exponential functions. F of x equals 5 to the x. The base here is 5. The next one, g of x equals 1 over 9 to the x. We could write this as 1/9 to the x power, because 1 to the x is also still 1. So our base for this one is 1/9. How about this one? H of x equals pi to the x. Pi is the base here, and x then is the exponent. Fill in the table and sketch the graph of f of x equals 4 to the x. So let's fill in the table. If x equals -2, we have 4 to the -2nd power, which is 1 over 16. So we have the point -2, 1/16. If x is -1, we have 4 to the -1st power, which is 1 over 4. That gives us the point -1, 1/4. If x is 0, 4 to the 0 power is 1. That gives us the point 0.01. If x is 1, we have 4 to the 1st, which is 4. And if x is 2, we have 4 squared, which is 16. Let's graph the points there that fit on our graph. So -2, 1/16, close to the x-axis there, but not quite there. -1, 1/4, 0, 1, 1, 4, and 2/16 is off our graph. So exponential functions have this basic shape. On the left side, the graph is getting closer and closer to the asymptote. The asymptote for an exponential function is the line y equals 0, or the x-axis. The domain for an exponential function is all real numbers. We can take 4 and raise it to any power we want. The range, however, is just from 0 to infinity, so all positive real numbers. If we take a positive number, like 4, and raise it to any power, we're still going to get a positive number. The y-intercept we can see is the point 0.1. So for exponential functions, if we have 4 to the x or 2 to the x, any number like that to the x power, then our domain is all real numbers. Our range is 0 to infinity. The asymptote is y equals 0, and the y-intercept is 0.1. Let's use transformations then of this graph that we have y equals 4 to the x to graph y equals -4 to the -x plus 2. Let's first think about what this would look like. The -x, this is going to reflect it over the y-axis. So then our line or our graph will look something like this. The -4, we'll flip it upside down over the x-axis. So then we would have something like this. And then the plus 2 will move it all up 2. So now we're going to end up with something like this. So let's actually graph a point or two. If I plug in the point 0, if we find the intercept, we have -4 to the 0 plus 2, which is -1 plus 2, or 1. So we have the point 0.1. The asymptote is actually y equals 2. And I know that because of this plus 2 at the end. Our asymptote is usually y equals 0. If we didn't have that plus 2 at the end, the plus 2 moves it up 2. If I plug in a point, let's say -1, I would get -4 to the -1st power plus 2, which would be -4 to the 1st power plus 2, or -2. So I have a point -1, -2. And I have a basic idea of what the graph looks like from on the left when I played around with it to see what the reflections on the plus 2 would do. So there is the graph of -4 to the -x plus 2. And here's the graph, computer-generated graph, and you can see that a little bit neater than the way I drew it, but it's the same graph. Let's look at the following, the domain. First of all, the domain is still all real numbers. We can raise any number to any power we want. That's still allowed. The range now goes from -infinity to 2. If I look at my graph, I can see that it goes down forever because it got flipped upside down, but then goes up to that asymptote, which is 2. The asymptote, the line y equals 2, we've already talked about that. And the y-intercept is the point 0.1. What about this one? If we change it to 1/4 to the x instead of 4 to the x, we'll plug in some points here. So if I have 1/4 to the negative second power, that's 16. So I have negative 2, 16. 1/4 to the negative first power is 4. So negative 1, 4. 1/4 to the 0 power is 1. So 0, 1. 1/4 to the first power is 1/4. 1/4 is that point. And 1/4 to the second power is 1/16. So the point 2, 1/16. If I graph those points, negative 2, 16 is off on my graph. But negative 1, 4 is right here. 0, 1, 1, 1/4, and 2, 1/16. And I know the basic shape here. Same shape, but this one is decaying instead of growing. So instead of going up from left to right, increasing, it is now decreasing from left to right. We still have the same domain. Domain of any exponential function is all real numbers. The range goes from 0 to infinity. The asymptote is still y equals 0, and the y-intercept is still the point 0, 1. So what makes this graph decrease instead of increase like 4 to the x did? That would be the 1/4, our base. That base is between 0 and 1, which means we are decreasing. If that base is bigger than 1, we are increasing. Show that the graph of y equals 4 to the x is the reflection of the graph of y equals 1/4 to the x across the y-axis. If we start with y equals 1/4 to the x, we reflect it across the y-axis. We have y equals 1/4 to the negative x, which I could write as 4 to the negative first power to the negative x, because 1/4 is the same as 4 to the negative first power, which is 4 to the negative first times negative x, which is 4 to the x. So if I take 1/4 to the x, that is the reflection of 4 to the x. You can see they're reflected across the y-axis. The one-to-one property of exponential functions says that if we have b to the m equals b to the n, then m equals n. So if we have the same base, b to some power equals b to some power, then those two powers have to be equal to each other. Notice that no horizontal line intersects the graph of an exponential function more than once. So an exponential function is one-to-one, which is why this property holds. Let's use this property to solve an equation. Solve the exponential equation 2 to the 4x equals 8. Right now, the way this is written, we do not have the same base, but I could write this as 2 to the 4x equals 2 to the third. 8 is 2 to the third, and now I have the same base on both sides, which means my exponents need to be equal to each other because the base was the same and the two numbers are equal. Divide by 4 and I get x equals 3/4. Let's solve this equation. 3 to the 7x equals 81 to the 4 minus 2x. The way it's written right now, we don't see the same base, but 81 is 3 to the 4th power. So I have 3 to the 4th and then 2 to the 4 minus 2x. So on the right side there, I can multiply my exponents. I have to distribute through to multiply them, so I get 3 to the 16 minus 8x. Now I have 3 to some power equals 3 to some power. I can set those two exponents equal to each other and solve for x. So I'll add 8x to both sides and get 15x equals 16. Divide by 15 and I get x equals 16/15. Let's try this one. I have 8 to the x equals 1 over 128. So 128 is 2 to the 7th power. And if you don't know that, you can play around with your calculator to find the right power, find the right exponent to write these as the same base. So if 128 is 2 to the 7th power, then 1 over 128 equals 2 to the negative 7th power. So I could rewrite this equation as 2 to the 3rd to the x power, because 8 is 2 to the 3rd, equals 2 to the negative 7th. So I have 2 to the 3x equals 2 to the negative 7th. So I have 2 as my base, 2 to some power equals 2 to some power. I can set my exponents equal to each other, and I get x equals negative 7/3.